Morning. Well, today what I'd like to talk about is the Regiochemical and Stereochemical course of E2 eliminations. And just as we learned with SN2 reactions that there were some very interesting stereochemical aspects dictated by the mechanism, we'll see that there are both stereochemical aspects and regiochemical aspects that come from the mechanism and from various thermodynamic factors in the E2 elimination reaction. Now, we've heard the term stereochemical before. By regiochemical, turn down the volume here. By regiochemical, I mean what region of the molecule the reaction occurs at. Let's take a simple example of this. And the example I'll take is just the elimination reaction of 2-bromobutane with sodium ethoxide in ethanol. Remember, we often write reagents over arrows and solvents under arrows. And we saw last time when we were talking about elimination versus substitution reactions that strong bases like alkoxides generally favor elimination rather than substitution with secondary alkyl halides. So we get a number of different products from this reaction. The alkane products that form are 2-butene. And we get two different stereoisomers. I'll come back to this in a moment because we've got many different aspects going on, but two different isomers of 2-butene, cis and trans 2-butene. These constitute the major product of the reaction. 81% of the alkane produced are these two isomers. We also get a minor product, another isomer of butene, this isomer being 1-butene. And we get less of it. We get about 19%. So as I said, there's a lot going on here. What I want us to be able to do is to figure out, to really understand this reaction. So first, let's just talk mechanistically what's going on. This is an E2 elimination reaction. A base is coming and pulling off a proton on the beta carbon, and then pushing in electron density to form a double bond and kicking out bromide. Let me show you what I mean. So for the formation of 1-butene, here's our molecule. We have a hydrogen at the 1 position. We have a hydrogen at the 3 position. For starters, let's look at what happens if the base approaches the hydrogen at the 1 position. So we have, here's our ethoxide. So electrons flow from ethoxide to the hydrogen. We can't have 4 electrons around the hydrogen, so we push electrons in between carbons number 1 and carbons number 2, but we can't have 10 electrons around carbon number 2, so we push out bromide. And at the end of the day, then, what we have, flip the orientation here, let me write it in the same way. At the end of the day, what we have is butene, 1-butene to be specific, plus ethanol, plus bromide anion. There are two different places that ethoxide can pull a hydrogen off. As I said, we can pull it off from the 1 position, but we can also pull a hydrogen, or more specifically a proton, off from the 3 position. So let me represent that as well. Here's one of the 2 hydrogens at the 3 position. Here's our ethoxide. Bromine. And in a very similar way, electrons flow from the ethoxide to the proton. We push electrons between the 2 carbons. And we kick out bromide. So there are a lot of different things going on here, and I'll come to issues of which isomer we get in a moment, and the various issues that are involved depending on whether you pull off 1 proton or another proton. You can get either the trans isomer or the cis isomer. And so just to give us a little bit of a feeling on naming compounds, you're going to learn more about alkenes and their nomenclature in Chapter 10, but this is an alkene. It's an unsaturated hydrocarbon. Unsaturated meaning it has a double bond. We call it 1-butene because the double bond is connected to the carbon at the 1 position of the chain. These 2 stereoisomers are stereoisomers of 2-butene because we have the double bond connected to the 2 carbon, and specifically this stereoisomer here, let me just get rid of my old mark here, is called trans 2-butene. And the stereoisomer here is called cis 2-butene. And the big difference is whether we have the substituents on opposite sides of the double bond, or whether we have the substituents on the same side of the double bond. So if they're on opposite sides, we refer to it as the trans isomer, and if they're on the same side, we refer to it as the cis isomer. So what's going on here? Let's talk about our substitution and the fact that we're forming 4 times as much of the 2-butene as we are of the 1-butene. So more substituted alkenes are more thermodynamically stable. Let me write this down. By more substituted, I mean that in the 1-butene, we have 1 group on the double bond, 1 alkyl group, and 3 hydrogens. So we have 1 substituent on the double bond. In the 2-butene, we have 2 substituents. We have 2 methyl groups on the double bond. And so it's more substituted, though it's more thermodynamically stable. Now, what that means is that when the base comes in to pull off a proton, we're going over an energy hump. And we're going to, at the point of that energy hump, the transition state, we're going to start to feel some of that product-like stability. Remember, at the transition state, we've gone halfway, or part way, I should say, between the reactant and the product. That means we've started to form a double bond, we've started to break a bond between carbon and the proton, we've started to break a bond between carbon and bromine, we've started to form a bond between the ethoxide and the proton. So at the transition state, you're going to be feeling the greater stability in the choice for going for the 2-butene stereoisomer, and that's going to translate to a lower energy transition state, an easier path to take. Let me jot this down. Say this greater stability is reflected in the transition state. Now, long before chemists knew about transition states or really had very good concepts of structure and bonding, phenomenologically this was observed by a Russian chemist. The greater preference for formation of an alkene was observed by a Russian chemist and reported in 1875. His name was Zaitsev. So you'll read in your textbook about Zaitsev's rule. Zaitsev's rule is just a fancy way of saying that the more substituted alkene product tends to form in greater amount. 2-butene forms more than 1-butene in this reaction. All right, let me amplify on what I was talking about with transition states and see if we can make a diagram that reflects what I just said on that blackboard about the greater stability of the transition state leading to the 2-butene. So let's imagine we think about an energy diagram, and I'll just draw a diagram like we've done in the past, where on our y-axis we have energy, and on our x-axis we have the reaction coordinate, that progression from reactants to products. And I'll put our reactant somewhere up here. We know that the reaction goes, in other words, it's downhill energetically. So I'll put our product here. More specifically then, I'll put our 2-bromobutane and our ethoxide on the left. And on the right, let's start by worrying about the formation of 1-butene. So I'll put our 1-butene over here, and ethanol and bromide, of course, are the other products. And so we can think about a diagram. Remember, the E2 reaction is a concerted reaction. We don't form any intermediate. Just like an SN2 reaction, it's a bimolecular reaction where 2 reactants come together, collide, go over an energy barrier, and give rise to products without the formation of any intermediate. And so we can think about it like so. Here's our transition state. Now, 2-butene, as I said, is more stable. There's a slight difference in stability between the cis and the trans. I'm not going to worry about it right now. I'll just draw out one stereoisomer. So it's going to be lower in energy. Everything else is equal. We have ethanol, we have bromide in both cases. We have 2 different isomers. We're forming a more thermodynamically stable isomer. If I want to make a transition state diagram, if I want to make an energy diagram for the formation of 2-butene, I'm going to do exactly the same thing. And you can see almost intuitively, if I'm trying to connect to a lower point, almost intuitively, I'm going to have a lower energy barrier. In other words, a lower energy pathway that's available to the more thermodynamically stable product. And so I think from a diagram like this, it's very easy to see it when the reaction bifurcates that we're going to get mostly the more thermodynamically stable product and less of the less thermodynamically stable product. The other thing, and I think again almost intuitively it becomes apparent when I make a diagram like this, is that the more energetically downhill reaction, the reaction that I've drawn with the dotted line, has an earlier transition state. I mean, this is almost intuitive. If I'm getting from here, from the reactants, to a low energy product, I've got to make that hump earlier. So what we're saying here is the reactant is going, the transition state is going to be even more reactant-like. The more energetically downhill reaction has an earlier more, let's say, reactant-like because as soon as the ethoxide gets near that proton, it's better able to pull it off, and so we're better able to get over the hump. There's a fancy name that you probably wouldn't learn in this class, but Buck and Johnny certainly learn in their graduate level courses. It's called the Hammond postulate, which basically allows one to judge if you've got a more downhill reaction, you're going to have an earlier transition state. If you have a less downhill reaction or even an uphill reaction, you're going to have a later transition state. And so you can get a little bit of a picture of what the transition state looks like. And this is called the Hammond postulate. All right, let's take a moment now to talk about our alkane stereoisomers. So when you have a cis or a trans relationship about a double bond, you have a situation where you have an isomer. You have two different molecules like cis-2-butene and trans-2-butene. The isomers have the same connectivity, but a different arrangement of atoms in space, and they're not enantiomers. So this is a case where you have diastereomers. So in this case, I'm going to draw out the structure very explicitly so we can see it and we can start to understand the nomenclature. The way in which we decide the stereochemistry of an alkane is we simply look at one half, so let's look at the half on the right, and say which substituent is more important, which substituent is the higher priority substituent. We learned rules about higher priority substituents. The higher priority substituent is a substituent first and foremost with a higher atomic number. We did this in RNS stereochemistry, in Coningold-Frelog stereochemistry. And then if you have to, you start to look at the substituents one over and branching. But here it's easy. We have a carbon and a hydrogen. Carbon's a higher atomic number, so we have a higher priority substituent here. And then over here, a carbon and a hydrogen, higher priority substituent here. Here, the higher priority substituents are on opposite sides. Of the double bond. By that I mean this one is on this side, this methyl is on this side. Since they're on opposite sides, we say this is a trans isomer, or more specifically, in this case, trans 2-butene. Now, normally we use trans when one of the substituents is a hydrogen on each side, in the case of a di-substituted alkene. There's a more general way that people express this for even tri-substituted and tetra-substituted alkenes, and that's to use a German term, E, or entgegen, which means on opposite sides. So another perfectly acceptable name for this is E2-butene. It's the more general name. But generally, when talking about di-substituted alkenes, two different substituents on the double bond, people will talk about cis and trans. And of course, by di-substituted, I mean di-substituted on opposite sides. If we had isobutylene, for example, we wouldn't be talking about it in the same way. There's no cis and trans here because we have two hydrogens here. So you can't say, oh, it's one side or the other, whereas here we have to say, all right, our methyls are on opposite sides. And then by comparison, we have the cis stereoisomer. And here we look at this, we say, all right, we're going to look at one side, and we say methyl is higher priority than hydrogen. Other side, methyl is higher priority than hydrogen. The two methyl groups are on the same side of the double bond. So this is a cis stereoisomer, this is cis-2-butene. And again, the more generic, the more general, I should say, descriptor that works with tri- and tetra-substituted alkenes as well is the German Z, which stands for zusammen, or together. So this compound can also be called Z2-butene. So here I'd say for cis or Z, higher priority substituents on same side. Thoughts or questions at this point? Great question. I'm drawing it flat. Alkanes are flat. So I can draw it flat like this, or I can draw it wedge coming out, or I can draw it flat like this. But this is trigonoplanar. This carbon is triple-planar, and both planes are coplanar with each other. So the substituents and the double bond together constitute a plane in alkenes. Is that what you were asking? Okay. Other questions? Really, that was a really important question because it's easy to lose sight of. Now, the big difference between carbon-carbon double bonds and carbon single bonds is carbon-carbon double bonds are locked. You can't rotate about the carbon-carbon double bond. The pi bond involves two overlapping p orbitals. If you wanted to rotate about that central carbon-carbon double bond, you would have to remove the overlap between the p orbitals. That process is very high in energy because you have to break the double bond. The double bond's about 60 or 65 kilocalories per mole in energy. You can't get that much energy from heat. You would need a very energetic photon, for example, UV, very deep UV light to do it. So alkenes are locked in their conformation, but alkanes rotate freely about single bonds. The energetic barrier to rotation about the carbon-carbon bond in ethane is 3 kilocalories per mole. That energy is overcome thermally very easily. The energetic barrier for having two methyl groups in butane rotate past each other is about 5 or 6 kilocalories per mole. That energetic barrier is overcome very easily. And the energetic barrier to a ring flip in cyclohexane is about 10 kilocalories per mole, and even that energy is overcome very easily at room temperature. So energies of 10 or even 20 kilocalories per mole get overcome at room temperature. Reaction energies, activation energies up to 25 or 30 kilocalories per mole get overcome. But it's an exponential relationship between energy and rate. So by the time you're up to 60 kilocalories per mole, nothing happens. All right. Let's talk a little bit about the stereochemical course of elimination reactions. And if I have a chance, I want to show you something really cool at the end with acyclic stereochemistry. But I'm going to start with something a little easier with cyclic stereochemistry. All right, so there are some very strict stereochemical requirements for E2 elimination reactions. And the requirement is that the hydrogen that's being removed, the proton that's being removed, is anti-periplanar to the leaving group that's leaving. So let me show you what I mean. Here's our framework of the molecule, and I'm skipping all of the substituents. Our hydrogen's going to come on the opposite side from the bromine. The carbon-hydrogen bond is opposite to the carbon-bromine bond. We'd say that there's an anti-relationship here. We'd say that elimination occurs in an anti-fashion. In other words, our ethoxide comes in. We're starting to pull off the proton. We put electron density back here. And you notice this is almost like backside attack in an SN2 reaction. Remember, in an SN2 reaction, our nucleophile is going to come in directly backside of the carbon and cause the bromine to leave as bromide, taking its pair of electrons. In an elimination reaction, our base is pulling off a proton on the adjacent carbon, but our electron density is effectively coming in backside. We're actually putting electron density into the carbon-bromine sigma star orbital that's and thus breaking the carbon-bromine bond. So, in other words, the bonds are going to line up in an anti-periplanar fashion. If I were to draw a Newman projection, what we would see is that in the reactive state, here's our bromine, here's our hydrogen, and I'll fill this out just by showing lines because I haven't specified our substituents. And our ethoxide is coming in, we're pulling off the proton, and we're kicking out the bromine. So the opposite of anti-elimination is syn elimination. And it's not absolutely impossible for the hydrogen and the bromine to come in on the same side. It's not absolutely impossible for it to occur, but it's much more difficult. So syn elimination is not absolutely ruled out, but it's much more difficult. In the discussion problems this week, I've given an example of syn elimination, but it's a very special example where it's occurring in an intramolecular fashion, where for all intents and purposes, the base that pulls off the proton is built into the molecule. But when you don't have the base built into the molecule, when you have it occurring in an intermolecular fashion, there's a very, very strong preference for anti-elimination to occur. Let me show you some of the implications of this in a couple of examples. All right, first example I want to give involves two stereoisomers of 4-tert-butyl, of 1-bromo 4-tert-butyl cyclohexane. So let us take the stereoisomer in which the bromine and the tert-butyl group are cis to each other. And let's take the stereoisomer in which the bromine and the tert-butyl group are trans to each other. In other words, in the top stereoisomer, the bromine is on the same face of the cyclohexane ring as the tert-butyl group. And in the other stereoisomer, the bromine, the trans stereoisomer, the bromine and the tert-butyl group are on opposite faces. Now remember, tert-butyl group is very special. It's going to, and the reason that chemists use it in studying reactions is it really, really wants to exist in the equatorial position. So there's a real specialness to it. All right, when we treat our first stereoisomer, our cis stereoisomer, with potassium tert-butoxide and tert-butanol, we get E2 elimination quite rapidly to give the alkene, to give 4-tert-butyl-1-cyclohexene. On the other hand, when we subject our trans stereoisomer to the same conditions, potassium tert butoxide in tert-butanol, the reaction occurs only very slowly. I'll write elimination very slow. Only about 1/500th the rate. So in one case, you mix them, you see elimination. In the other case, you mix them, you see very little elimination, and you have to heat it and beat on it to make it go. What's the big difference? In the first case, the stable conformation of the molecule has our tert-butyl group, equatorial. The bromine's on the same face of the double bond of the ring. So the bromine is axial. Well, look at our adjacent carbon, our beta carbon. Our beta carbon has a hydrogen on it that's anti-periplanar. So we have an anti-periplanar relationship here. It's very easy for the ethoxide to come in, pull off the proton, push the electron density in to form a double bond, and kick out electrons onto the bromine to get bromide. You look at the cis stereoisomer, you look at the trans stereoisomer, and again, the tert-butyl group wants to be equatorial. Now, the bromine can be equatorial. That's a little bit more thermodynamically stable. But on the other hand, there are no hydrogens that are anti. You have one hydrogen that's gauche and another hydrogen that's gauche, but you have no anti-periplanar relationship. As a result, it's very hard to pull off that beta proton and to do an E2 elimination. Thoughts or questions? Look at another example, and I want us to now look at an acyclic example rather than a cyclic example. This is going to be a little bit harder to see because we're going to have to be visualizing some molecules that have flexible chains in them where you can rotate about single bonds rather than rings where it's very easy to see some stereochemical relationships. But this one is also very cool. I want to start with two different stereoisomers of 1,2-dibromo, 1,2-diphenyl-ethane. So I'm going to start with the chiral stereoisomer. I'll draw out the 1s, 2s stereoisomer of this chiral compound. I could also draw out the 1r, 2r stereoisomer. And we're going to see if we treat this stereoisomer with potassium terbutoxide and terbutanol. Just like in the other examples we've looked at today, taking a secondary alkyl halide with a strong base like ethoxide or terbutoxide leads to an E2 elimination reaction. What's interesting about this E2 elimination reaction is we get a single stereoisomer of the alkene. And that stereoisomer has the E geometry, the Z geometry. So the stereoisomer we have here is Z1-bromo 1,2-phenyl diphenylethane. It's Z stereochemistry because on this side of the double bond, we have a phenyl group. Remember, a phenyl group is a ring of 6 carbon atoms with alternating double and single bonds. So we have a carbon at this position, and at this position, although I haven't drawn it, we have a hydrogen. So carbon is higher priority. On this side, we have a bromine and a carbon. Bromine is higher priority. So bromine and carbon are on the same side, so we say that this is the Z stereoisomer. Now, I want to contrast this with what happens if we take the diastereomer of 1,2-dibromo diphenylethane. So I'm going to draw out the mesodiastereomer. And we're going to treat the mesodiastereomer with potassium terbutoxide and terbutanol. One sec. Ah, thank you. Ethene. Z1-bromo 1,2-diphenylethene, E-N-E, because we have the double bond. Thank you. And now we generate the other alkene diastereomer. So now, instead of ending up with the Z product, we end up with the E product. And just for the sake of being complete, I'm going to draw in the hydrogens here because we're going to see their fates in just a moment. So this is the E1-bromo 1,2-diphenylethene. All right, let's see how the two different products arise. The one product that comes from the 1s, 2s isomer, and the other product that comes from the meso isomer. Now, the easiest way, I think, to see the stereochemical course of this acyclic reaction is to draw a Newman projection and to look at the relationships of the hydrogens and the bromines. So I'm going to take the molecule on top, and I'm going to imagine picking it up and bringing it over like this. Let me show you again. The two bromines are pointing out. There's a phenyl group and a phenyl group. The bromines are pointing out. I'm going to pick it up and make a Newman projection. Can you see in your mind's eye what I just did? Here was the molecule. The bromines are coming out at us. One phenyl is up here, one phenyl is down here. I picked it up just like we've done in our discussion of visualizing stereochemistry. Brought it over here. Here's the phenyl that was on the top right. Here's the phenyl that was on the bottom left. And the two bromines are pointing over here. Now look how we're set up. In this rotamer, we're set up with a hydrogen that's opposite to a bromine, and another hydrogen that's opposite to a bromine. And I can do this with either hydrogen, it doesn't matter. I'll just have the ethoxide pull off this one. You'll get the same result if you pull off the other one. So we're going to pull off that proton, push in electron density, kick out bromine, and go to the alkene. And I'll draw a Newman projection of the alkene. We now have our phenyl group on front and our bromine on front. And then on back, we have a phenyl group. And remember, when things directly overlap, you offset them just a little bit in making your Newman projection drawing. And here we have a hydrogen. So do you notice now, if I just take this up and pick it up, pick it back up, here we have the product that I've drawn on top. In other words, this requirement for an anti-elimination gives rise to the stereoisomer that I've shown over on top, the Z stereoisomer. Let's try the exact same operation with the drawing of the meso compound. I'm going to take this molecule, pick it up, bring it over to a Newman projection. So we had a phenyl group here, a phenyl group here, a bromine on what's going to become the front carbon coming out at us, and a bromine on the back carbon going back. So this is a Newman projection of the molecule as I've drawn it on the bottom center board. Now, in this particular rotamer, there's no anti-periplanar relationship. This hydrogen is opposite to that hydrogen, and there's no anti-periplanar relationship between a hydrogen and a bromine. This hydrogen's opposite to that hydrogen. The two bromines are opposite to each other. But not a problem. As I said before, rotation about carbon-carbon single bonds occurs quite readily. And so we rotate through all different rotamers. You have a dynamic equilibrium. I'll just draw one other rotamer. I'll rotate the backside of the molecule. And so I will draw a rotamer. We'll just picture rotating counterclockwise about the back carbon. That's going to put the phenyl up here, the bromine here, and the hydrogen down here. In this rotamer, we do have an anti-periplanar relationship between a bromine and a hydrogen. This hydrogen is anti-periplanar to this bromine. Ethoxide base can come in, pull off that proton, kick in electron density to form a double bond, and give rise and kick out bromine. And this gives rise to this product. Now the two phenols are on the same side of the double bond. And this phenyl is opposite to bromine. In other words, I can just draw this molecule, flat, pH, pH, bromine, hydrogen, and you'll notice that we have the E stereoisomer. So the requirement for an anti-periplanar elimination has led to the Z stereoisomer in the case of the first diastereomer of dibromo-diphenylmethane, and the E stereoisomer in the case of the second. In our final class, we'll pick up and we'll talk about E1 eliminations and conditions under which they occur.